What happens when artificial intelligence literally just runs out of data? It's a question that is absolutely keeping top researchers awake at night.
Welcome to the Hidden Layer Decoding Artificial Intelligence. I'm your host, and today we're unpacking a groundbreaking research paper to show you exactly how to apply its findings in the real world. We are decoding the Simula framework.
Over the next few minutes, I'm going to give you the exact blueprint for generating perfect synthetic data to build a highly specialized, verifiable AI agents. If you're an applied engineer, this is your ticket out of the data bottleneck. Oh, and make sure you stick around because I'm opening a loop right now. Later in this explainer, I'll reveal a secret mathematical technique from the paper that lets you dial up the exact difficulty of your training data without breaking your dataset. All right, let's dive right into Section 1, the data scarcity crisis. So let's face the massive problems staring applied AI engineers in the face right now. We are hitting a wall. Our field's total reliance on real-world data is creating this enormous economic threshold that's just marginalizing everyday developers. Relying purely on human annotated data is prohibitively expensive, it's super slow, and frankly, it forces a purely reactive approach to safety. I mean, think about it. With real data, models can only be hardened against rare edge cases after a failure is actually observed in deployment. For safety-critical systems, that is a completely untenable practice. But contrast that with a synthetic-first approach. It's programmable, inherently scalable, and totally controlled. It literally flips a black box headache into a transparent white box pipeline. Okay, so how do we fix it? That brings us to Section 2, the Simula framework solution. So how do we actually build this programmable pipeline? Enter the solution, Simula. It's a reasoning-driven framework that uses a seedless, agentic approach to generate synthetic datasets at massive scale. Now, why do seedless and reasoning-driven actually matter? Well, existing synthetic generation methods usually rely on extensive seed data, manual prompts, or these incredibly opaque evolutionary algorithms. That just limits your control. Simula builds data from first principles. It ensures that the generation capabilities naturally improve right alongside the underlying AI models as they get better at reasoning. As the researchers perfectly note here, the static nature of real-world data slows down development cycles, in stark contrast to the programmable workflows that a synthetic-first approach enables. This right here is the paradigm shift. You are no longer mining for data. You are engineering it. You're writing the code that dictates the reality your model's going to learn from. Which naturally leads us to Section 3, mapping data with taxonomies. So how do we actually implement this? First step, map out the conceptual space. Now, what's really interesting about this slide is if you look at the flow on the left, just asking an AI to generate a data set of stories about cats, you basically just get random sampling. You end up with these massive clusters around common concepts, and you totally miss the edge cases. It has zero notion of a global coverage space. But look at the flow on the right. Simula uses taxonomies. It breaks the concept all the way down. Cat type becomes domestic, which becomes short hair, which becomes British short hair. If you want a data set about a red cat on a couch, you absolutely need a system that systematically maps out cat breeds, colors, and environments to ensure perfect global coverage. To prevent what we call coverage loss, like accidentally missing the entire small wild cats branch, Simula uses a multimodal model, or M3, capable of processing text and images to propose factors of variation. It expands these breadth first. But here is the absolute genius part. It uses best of N sampling, generating multiple options and picking the absolute best to cast a wide net. Then, it literally employs an AI critic to iteratively refine the taxonomy tree. The critic adds, merges, or edits nodes to ensure total completeness. Essentially, it maps the DNA of your dataset before a single data point is even generated. And now, the moment you've been waiting for, Section 4, the secret, agentic refinement. Yep, it's time to close that loop from the introduction and reveal the specific pipeline that guarantees top-tier quality. Once you have your taxonomy map, you orchestrate generation using an architecture like the IGNE framework. IGNE provides the real-world implementation structure for these 4 actionable steps. First up, taxonomic sampling. The IGNE agent creates a mix, and crucially, it actively prevents illogical combinations. It is not going to mix a toddler audience tag with a horror theme tag. Second, it turns these mixes into diverse meta-prompts. Third is complexification. And fourth is critic evaluation, where a dual critic filters the actual generated data for quality. Let's zoom in on step 3, because this is huge. So the crucial point is this concept of complexification. Simula allows you to inject constraints or edge cases into a user-defined fraction of the metaprompts. It's basically a dial you control. You can intentionally make the data more confusing, uncommon, or elaborate. If you need a ridiculously difficult dataset to train a highly specialized model, you just turn up the complexity knob for specific data factors, and you do it without poisoning or breaking your entire dataset. And this brilliantly illustrates exactly why all of this effort is 100% worth it. For the data scientists watching, check out this chart showing downstream accuracy on the CTMCQ benchmark. That bottom line, that's your baseline. As you scale the data from 4,000 all the way to 84,000 samples, the baseline barely improves. But look at that top line. That is the full Simula system utilizing the global taxonomy maps and those agentic critic loops. Adding these reasoning first steps definitively and consistently boosts downstream model accuracy. The proof is right there.
All right, bringing it all home, Section 5, Building Verifiable AI Agents.
So, let's connect all this theory back to practical application for you, the builder. By utilizing a framework like Simula, applied engineers immediately escape the crippling economic threshold of manual annotation. You can now build massive datasets for auto-verifiable tasks, like complex coding or advanced math reasoning, at a fraction of the cost. Because you have a transparent audit trace of how every single data point was made, your specialized agents are highly controllable and verifiable. And you get fine-grained control over your compute, meaning you only allocate resources to the specific edge cases your model actually struggles with.
We are officially moving from an era of data mining to an era of data design. So, if programmable, reasoning-driven synthetic data dictates the next massive leap in artificial intelligence, what specialized, verifiable agent are you going to build first? Let me know your ideas in the comments below. Thank you so much for joining me on this explainer, and I will see you in the next decoding session on the hidden layer.